This video is going to make some waves. You've got the basics of vertex displacement, and now it's time to take it to the next level. We'll be making some circular waves on a plane, like something impacted the water, like a raindrop, for example. And we'll be making some linear waves, which are surprisingly more challenging than those circular waves. Hey, Chris here from LlamAcademy. Here to help you.
Who, me?
Yes, you! Make your game dev dreams become reality by making waves in ShaderGraph. For this one, I expect you've already used ShaderGraph before. You kind of know what to do, at least from an interaction point of view. If you're brand new to ShaderGraph, you might want to go back to the last one where I take it a little bit slower and explain exactly what we're doing in an interaction point of view. There's a link in the description and card on the screen for that video. Let's jump in and make some waves. We'll start with the circular wave displacement. Surprisingly, this is the easier one. I pulled the formula for how we do this from NVIDIA's GPU gems, which you can see on screen right now. This is the formula we're going to implement. The key formula is we're going to set the y position to be y plus the value of sine computed at u times the square root of x squared plus z squared, and then adding in n, where u is the frequency parameter, which is going to be an option on our shader, and n is the phase parameter, which we're just going to set to be time times speed, and we're using a negative value for that. A couple of quick notes. If we use a low poly plane like this one, where this one's like 4 quads glued together, this isn't going to look right because we're going to be trying to do waves and we need to have vertex manipulation. If I only have like, I don't know, however many vertices this is, 9 vertices isn't going to animate very well. So if we replace it with a high poly plane like this, that I very expertly modeled in Blender but couldn't figure out how to make Y be up, it'll animate much better. This high poly plane is included in the repository. Just remember that it's like this, which doesn't work very well for us, so we have to rotate it 90 degrees, which will impact a little bit the values we use for X and Y quotes in our formulas. We open up our circular wave displacement shader, which I've chosen as a URP lit shader. That's not super important for this. I'm going to quickly add some video editing magic so we get the base input. We're not going to worry about re-implementing that now. Hopefully you already know how to do that. If not, check out one of my last 2 videos where I went over how this exactly works. Now, based on our formula, we know that we need at least one parameter, u, the frequency, which should be a float value. I'll set that to have a default value of 1. Since this formula requires us to have x, y, and z positions, let's go ahead and grab the object position. We need those to be split because we need to independently use x, y, and z. I'll take the x and the y, meaning the r and the g components here, and attach them to a power node, taking them to be the second power. If you're using a plane that's correctly oriented, you'd probably want to use the r and the b, which corresponds to x and z, because we're going to manipulate it up and down on the y. These two are added together, and then we take the square root of them. And then the formula said we're going to multiply this by the frequency. The next piece was the phase parameter, which we want it to be automatically animated. If you want to control this with a script, you could add a new float to be the phase, and then set this however frequently you want to set it. I'll add a speed parameter, set the default to be 1, multiply it by the time parameter, negate it so it flows out from the center instead of in towards the center. Negate just flips the sign effectively. We'll add that negated value to the last multiply that we did below. Do a little rearranging. Hook up that add to a sine. We'll add the sine to the b, which is the z value, and again, that's just because our plane is rotated. You may want to use the g, which corresponds to y instead. Do a little rearranging. We'll combine our outputs with the add here, going into the b, which corresponds to z, and the r and the g, the x and the y's, back into the r and g's respectively, and take our output here into the vertex output position. If we save our shader, come back to our scene view and change our shader of the water material to be our circular wave, that's super cool, and you can see why it's very important to have a high poly mesh for us to use. So looking like it moves pretty slow, so let's adjust the properties. Moving it to 3 makes it look a little bit cooler. If we adjust the frequency, we'll see more or fewer waves as we increase and decrease it. That's pretty awesome, huh? Circular displacements work really well if we're talking about like raindrops or a plop into an ocean. You'd be able to apply this kind of math to offset the positions of some vertices relative to that impact point. Now let's take a look at linear wave displacements. For this one, I have as clean of a reference point. I kind of played around based on this formula, where the y value should be the y value minus the amplitude times sine of x times the frequency minus n, where n is again the phase parameter, and we're going to do basically the same thing as we just did. So we'll start off the exact same way, taking our position and splitting it, remembering to change it to object space. We'll then make those inputs. We have frequency, amplitude, and speed. We'll set up some defaults, speed to be 1, amplitude to be 0.25, and frequency to be 1. We'll then take the r, which corresponds to x, multiply by the frequency, subtract from that n, and remember from before, n was our phase parameter, so we'll do time times speed. This time, since we're subtracting, we don't need to negate it. We'll pipe that into a sine. We'll multiply the output of that by the amplitude. And finally, subtract the y value. In our case, because our plane is rotated, we're going to use z again. Subtract this value from the z value. Finally, we'll combine all of these together and pipe that out to the position on the vertex. We'll save this asset, hop back to the scene view, and apply it to our material as the shader. Cool. Now we can see waves going across in the x-axis based on our speed, frequency, and amplitude. It'd be nice to also be able to specify the direction, so maybe we could have it going faster in the y, or go to -x, or even control that with a script. Right now it's only going in the x direction. To do that, we're going to apply basically the same concept, but using both the x and the z, or in this case, the x and the y coordinates. We'll right-click, create ShaderGraph, SubGraph, and name it Wave Y Offset. A subgraph allows us to basically group a bunch of quote code unquote together, or a bunch of nodes that perform the same operations, so we don't have to tie them all together and copy paste a million nodes. It's kind of like adding a function call to group code together. In this case, that offsetting logic is going to be the same, we just want to use the z instead of the x, or the y because our plane is rotated instead of the x. As input, we need a float position, a float frequency, a float speed, and a float amplitude. What we can do is copy the vast majority of these nodes over to that subgraph and take our final multiply to our output. Then just bring our position node and multiply by the frequency. Pretty cool. If we save this, in our linear wave displacement shader, we can then add a wave Y offset subshader node. We'll then drag in again frequency, speed, and amplitude from our shader graphs panel, hook them all up to the inputs of the wave Y offset, and hook the R node up to the position. And hook the output to the subtract B node. All we've done there is taken all those nodes, put them into a subgraph, and hooked up the inputs and the output. If we save this again, we'll see everything's working exactly the same as before. That's pretty cool. Now in our linear wave displacement, we can do the same thing using the G as the position. I'll copy paste the wave Y offset. It retains all of the hookups, so I'll delete the one coming from R and attach the one for G. Again, in this case, you might use B, which corresponds to Z if your plane's not rotated. We'll again subtract out the B value, add the two outputs of these wave Y offsets together, and hook them up into the B of the combine. All we've done here is duplicated the same process we were doing on X on the Y, or the world Z. If we hop back into the scene view, we can see now we have waves going in two directions. They're going in the positive X and positive Z axis. But I still can't control these. So back in linear wave displacement, we have one last step to do. Let's add in a new input, direction, that's a vector 2. We'll split it, take the R and multiply it by the R coming in from the object's position. And the G times the G coming in from the object's position. With that, we should be able to control the direction of these waves either in the inspector or in code. We can elongate the waves by putting a very small value for y or x. So from here, I think you can start seeing how at least the fundamentals work for how we would add waves to water. Real waves are significantly more complex than this, so we're not going to get too much into those today, but you can get at least maybe a low poly style wave working with this simple calculation, or even by adding in some noise into the mix. I hope you got a lot of value out of this video, and if you did, make sure you've liked and subscribed to help the channel grow, reach more people, and add value to more people. And if you want to support this channel, you can go to patreon.com/LlamAcademy, or click super thanks or join right here on YouTube. Get your name up here on the screen, get a shout out starting at the awesome tier, and some other cool perks too. At the awesome tier, there's Gerald Anderson, Autumn K, Matt Parkin, Ivan, Rulin, Ippy Obelisk, and Fernando. At the tremendous tier, there's Bruno Bozic. And at the phenomenal tier, there's Andrew Bowen. Thank you all for your support. I'm so incredibly grateful.